Welcome back everyone to an introduction to neural networks. We've seen how a single perceptron behaves. Now let's expand on this concept to get the idea of a neural network. Let's see how to connect many perceptrons together and then how to represent this mathematically. So what does a multiple perceptrons network actually look like? Well, essentially looks like this. Here we can see that we have various layers of single perceptrons connected to each other through their inputs and outputs. In this case, we have an input layer all the way on the left, which is purple. We have two hidden layers, and hidden layers are the layers that are in between the input layer and all the way on the right, that output layer. Essentially, hidden layers are layers that don't get to see the outside, that is, all the way the inputs on the left or all the way the outputs on the right. So input layers, those are real values from the data, so they take in the actual data as their input. Then you have hidden layers, and those are the layers between the input and output layers. And if you have 3 or more hidden layers, that's considered a deep network. And then an output layer where you have some sort of final estimate of whatever the output that you're trying to estimate is. So as you go forwards through more layers, the level of abstraction increases. Let's now discuss the activation function in a little more detail. Previously, our activation function was just a really simple function that output 0 or 1. Remember, we were just taking the sum of the inputs in that simple perceptron model and then had an activation function that just had an output of either 0 or 1 based off whether the number was positive or negative. And if we plot that out, that looks like this. We can say the output is either 0 or 1 on the y-axis, and then on the x-axis we see our marking at 0, and if we have a negative value, we output 0, and if we have a positive value, we output 1. And we did this by having the x-axis be wx plus b. That is the weights times the inputs plus that bias. And it's really common to just set that equal to z, so you can refer to z instead of having to constantly refer to wx plus b. So whenever I say z, I'm essentially referring to those weights times those inputs plus that bias. So unfortunately, this is actually a pretty dramatic function since small changes aren't really reflected. So you can have kind of really small changes in z. For instance, the change from 0.5 in z to 0.6 doesn't really matter. It's still going to output 1 as long as it's positive. Or the change that are really dramatic from -1 to -1000 doesn't really matter. It's going to be 0. So it'd be nice if we could have a more dynamic function. For example, this red line here. You can see here that our outputs now are no longer just 0 or 1. We have a little more detail to it. There's a little more nuance here. So lucky for us, this is actually the sigmoid function. This red line function already exists, and it's known as the sigmoid function. And the sigmoid function is just f of x is equal to 1 over 1 plus e to the negative x. And we could replace x here with z. So we have z is equal to wx plus b. So we just take that whole thing, that z, and plug it into the sigmoid function. So we'd have f of z is equal to 1 over 1 plus e to the negative z. And that would be our sigmoid function for the activation function. So changing the activation function used can actually be really beneficial depending on the particular task we're trying to complete. And we'll get into more detail on that later on when we actually implement our own neural networks. Let's discuss a few more activation functions that we're going to encounter throughout this course. So a really common function that's used as an activation function besides the sigmoid function is the hyperbolic tangent function, or tanh, or tanh of z, where z, remember, is just wx plus b. And that looks really similar to the sigmoid function, except note that the output can then be from -1 to 1, unlike previously we had 0 to 1. So if we look at the sigmoid function again, that went from 0 to 1, and that was equal to 1 over 1 plus e to the negative x or negative z, whatever the input is. And now for the tanh, or hyperbolic tangent function, it goes from -1 to 1, but still has that sort of same behavior shape. And if you're interested in how to express the hyperbolic tangent mathematically, over here on the right-hand side are the actual equations for it. Then there's also the rectified linear unit, or ReLU, and this is a really common activation function, but it's actually relatively simple. And the way it works is the following method. You basically pass in your z value into this max equation. So you say max of 0 or z. So what does that actually mean? Well, the rectified linear unit, that actual activation function, works the following manner. It says based off your z value and 0, just return the maximum value. And that actually means that if your value of z is negative, then the max between 0 and any negative number is always going to be 0. So we can see here that as z, if it's negative, the function always returns 0. And then between max 0 comma z, if the z is positive, it's always going to return the value of z. So essentially you have just y is equal to z here. So on the right hand side, that's why you get that sort of straight linear line. So again, relatively simple function, but this is kind of considered at certain points in time state of the art. So we're going to definitely be seeing this activation function a lot throughout our lectures. So that rectified linear unit and hyperbolic tangent tend to have the best performance, so we're going to really focus on these two throughout the course. But deep learning libraries in general have these built in for us, so we don't really need to worry about having to implement these activation functions manually. We'll essentially just be able to select them from our deep learning library. As we continue on, we'll also talk about some more state-of-the-art activation functions. But up next, what we're going to do is discuss cost functions, which will allow us to measure how well these neurons are actually performing. So right now, we've understood two major concepts, the perceptron and then the activation function inside that particular neuron. Up next, we'll discuss cost functions. Thanks, and I'll see you there.